There was a time when every American machine shop contained tools that required a steady hand, patient eyes, and years of practice before a man could use them without ruining the work. He did not learn these tools from a manual. He learned them by standing next to an older machinist, watching him set up a job, and being handed the simple tasks first, filing a burr, holding a part steady, sweeping the floor, until one day he was trusted with the real work. Most modern men who walk through a machine shop today would not recognize half of what hung on the wall in 1950. Not because the tools were replaced by something better in every case, but because the patience required to use them well disappeared along with the men who taught it. Number 9 is a tool so simple that most people would walk past it without a second glance, yet it represents one of the oldest ideas in precision work. Let us get into it. Number 9. The spring caliper. Before digital calipers, before dial indicators, the machinist who needed to transfer a measurement from a steel ruler to a piece of raw stock reached for a spring caliper, 2 curved legs, a tension spring at the top, and a small adjusting nut that let a man dial in a measurement down to a fraction of an inch and lock it there. He would set the legs against the ruler, tighten the nut until the spring held the gap firm, and then walk over to the workpiece and scratch 2 marks exactly that distance apart. The beauty of the tool was its repeatability. A man could set a spring caliper once and use that same setting 40 times across a shift without it drifting. The hand had to be steady, the eye had to be turned with a light touch, not a heavy one. A man who turned the nut too fast would overshoot the mark every single time, and he would never quite know why his measurements were drifting until someone older showed him to slow down and feel the spring tighten under his fingers. By the time digital calipers became cheap, the spring caliper became a draw item, pulled out only when the batteries died. The measurement did not change, the hand that trusted itself to hold it did. Number 8. The expanding mandrel. Any machinist who has tried to turn a hollow cylinder on a lathe knows the problem immediately. You cannot grip a tube the same way you grip a solid bar, because the chuck jaws will crush it or hold it off-center. The expanding mandrel solved this from the inside. It was a tapered shaft, often split into segments, that slid into the bore of the workpiece, and then expanded outward when a nut was tightened on the end, gripping the inside walls evenly all the way around. This let a man turn the outside of a ring, a bushing, or a sleeve with the piece running perfectly true, no wobble, no crushed edges. Setting up an expanding mandrel correctly took real feel. Too loose and the part would spin on the mandrel and ruin the cut. Too tight and the part would crack or seize permanently onto the tool. And a seized part on an expensive mandrel could cost a man an entire afternoon of careful work just to free it again without damaging either piece. A machinist learned the right amount of tension the same way he learned everything else, by ruining a few parts early and remembering exactly how that felt in his hands. Decades later, the same man could chuck up a mandrel, give the nut a quarter turn, and know by feel alone whether the part was gripped correctly, without ever touching a gauge. Number 7. The hand vise. Small enough to fit in a coat pocket, the hand vise looked almost like a metal pair of pliers with a wing nut threaded through the middle of the jaws. A machinist used it to hold tiny parts, pins, screws, small brackets, anything too small to clamp safely in a bench vise without crushing it or losing it entirely. He would slip the part between the jaws, spin the wing nut down by hand until it held firm, and then file, drill, or polish the part while holding the whole assembly steady against the bench or even braced against his own body. The hand vise was personal in a way larger tools were not. Most machinists owned their own, kept it in a pocket or a small drawer, and the jaws would slowly wear to match the kinds of parts that man worked on most often. A young apprentice's hand vise looked clean and unworn. An old machinist's hand vise had a story in every scratch, every worn corner a record of some part he had filed 1,000 times before he ever got it right. Some men carried the same hand vise for 30 years, through 2 or 3 jobs and 1 or 2 shops that closed down around them, because a good one never wore out. It only wore in. Number 6. The lead or copper mallet. Steel hammers were everywhere in a 1950 shop, but for certain jobs, steel was the wrong choice entirely. When a machinist needed to seat a hardened pin into a bore, drive a bearing partway onto a shaft, or knock a stuck part loose without leaving a single mark, he reached for a mallet with a head cast from soft lead or copper. The soft metal absorbed the shock of the blow and deformed slightly against the workpiece instead of denting it. A man swinging a lead mallet had to relearn how to hit something. The mallet head would mushroom out over time from repeated use, and a good machinist would periodically cut the deformed face flat again with a hacksaw so the striking surface stayed true. Some men kept 2 or 3 mallets of different weights lined up on the bench, one for delicate brass fittings, one for heavier bearing work, and could reach for the right one without looking, the same way a carpenter reaches for the right chisel. The skill here was restraint. Any fool could swing a steel hammer hard. It took a trained hand to swing a soft mallet with exactly enough force to move a part and not 1 ounce more. Number 5. The leg vise. This was not a small tool. The leg vise was a heavy iron work-holding device, often older than the man using it, with one solid iron leg running straight down to the floor where it was set into a block of wood or stone. Unlike a modern bench vise bolted only to a tabletop, the leg vise transferred the shock of heavy hammer blows directly into the floor itself, which meant a blacksmith or machinist could clamp a piece of red-hot iron in the jaws and strike it with full force without the vise walking across the bench or shaking itself loose. Opening and closing a leg vise took a different motion than a modern vise. A wooden handle on a screw turned the jaws, but the leg vise also had a spring bar at the back that kept the jaws open slightly even when not in use. So a man could slap a piece of stock into the rough position and then tighten down quickly instead of winding the screw open from a fully closed position every time. The leg vise also had a particular sound, a deep ringing clang when struck, different from the dull thud of a bench vise, and old machinists claimed they could tell from across a shop floor whether a man was working iron or just fiddling with something small. Shops that had electric power hammers eventually retired their leg vises to the corner, but the old-timers kept theirs close because some jobs still needed that much iron under your hands. Number 4. The taper pin reamer. Many machine assemblies in 1950 relied on a simple but elegant idea, the tapered pin that could work loose over time from vibration. A tapered pin was driven into a slightly tapered hole, and the deeper it went, the tighter it gripped, until the two surfaces locked together by friction alone with no threads and no welds. To create that tapered hole correctly, a machinist used a taper pin reamer, a conical cutting tool with fluted edges running down its length. He would start with a straight drilled hole slightly undersized, then turn the reamer in slowly by hand or at low speed, checking the fit against the actual pin every few turns. Go too far and the hole was ruined, too loose for any pin to grip properly, and there was no fixing it short of starting over with a larger pin entirely. Many shops kept a small wooden box of taper pins in graduated sizes just for this reason, because every reaming job was a small negotiation between the reamer and the pin, and a careful man always checked twice before committing to that final pass. The taper pin reamer rewarded patience and punished rushing in a way few other tools did, because the mistake was invisible until the moment the pin slid in loose, and the whole job had to be scrapped. Number 3. The engine turner. Of everything on this list, the engine turner produced the most beautiful results from the least glamorous process. This was a hand-cranked engraving machine, often built like a small lathe with a rocking cutter mounted above the workpiece, used to cut fine repeating geometric patterns directly into metal. A watchmaker or instrument maker would clamp a brass or steel plate into the machine, set the cutter depth, and then turn a crank by hand while guiding the workpiece in a controlled path, producing patterns of overlapping circles or straight engine-turned lines that caught the light from different angles. The patterns now associated with fine watch movements and decorative metal plates were made this way. one careful crank at a time by a man whose rhythm had to stay perfectly even from the first pass to the last. A single jerky crank, a single moment of distraction, and the pattern would show a flaw that no polishing could hide. Some men spent years before they were trusted to engine turn a customer's plate at all, starting instead on scrap brass until their crank speed became as steady and unconscious as their own breathing. The engine turner did not reward speed. It rewarded a steady hand repeating the same small motion hundreds of times without variation. Number 2, the brace and bit. Before the cordless drill, before even the electric drill, the brace and bit was how a man bored a hole through wood, or, with the right bit, through thinner steel and brass stock. The tool looked something like a crank handle bent into a wide loop, with a chuck on one end to hold the bit and a knob on the other end that the man pressed against his chest or stomach while he turned the crank with both hands. What made the brace valuable was not speed, but torque and control. A man could feel exactly how much resistance the bit was meeting, slow down the instant the bit began to bind, and back it out before it snapped. There was no trigger to release, no motor to overheat, just the steady push of his body weight and the steady turn of his arms working together. A skilled man could bore a clean, straight hole through thick stock using nothing but his own strength and his own sense of how the metal was responding underneath his hands. Boys learned on the brace before they were allowed near anything with a motor, because the brace could not hurt you in the same way, and a slow mistake with a brace was just a slow mistake, not a torn hand. The cordless drill does the same job in a fraction of the time, but it removed the feedback. The hole gets made, the feel of making it is gone. Number 1, the scriber and layout die. This is the tool that contained all the others, the one that came before every cut, every drill, every weld in the entire shop. A machinist would coat a piece of raw stock with a thin layer of dark blue or purple dye, let it dry to a dull matte finish, and then take a hardened steel scriber, sharp as a needle, and scratch lines directly into that coating to mark out exactly where every hole, every cut, and every bend needed to go. The scratched line cut through the die and exposed the bright metal underneath, creating a permanent, exact guide that no amount of handling or oil could smudge away. Before computer-aided design, before laser cutters that could trace a digital file onto steel in seconds, this was how a complex part began its life, as a set of hand-drawn lines scratched onto a dyed surface by a man working from a blueprint, a steel ruler, and a center punch. Every measurement had to be right the first time, because there was no undo. A wrong scratch on a dyed plate was a wrong scratch forever, and the part either got worked around it or got scrapped. A good layout man was respected the way a good surgeon is respected, because everyone in the shop understood that his lines were the difference between a part that fit and a part that became scrap metal by the end of the day. The scriber was cheap. The die cost almost nothing, and yet this combination was the foundation underneath every precise metal object made in that era. Nothing got built correctly until a man had first marked, by hand, exactly where it needed to be. Notice what runs through every tool on this list. None of them were complicated, none of them required electricity, and most of them required almost no money at all. What they required was a hand that had done the same motion enough times to know, without thinking, exactly how much pressure was too much and exactly how much was not enough. That sense, built slowly over thousands of repetitions, is what disappeared from American shops, not the tools themselves. A young man today can buy every single item on this list for less than the cost of one modern power tool, and most of them will outlast anything plugged into a wall. The brace still bores a hole. The leg vise still holds iron steady. The scriber still scratches a perfect line into dyed steel. The engine turner still cuts the same patterns it cut 100 years ago, and the spring caliper is still as accurate today as it was the day it was forged. The tools are still out there, in barns, in estate sales, in the back corners of shops that never got cleaned out, waiting in toolboxes that smell like oil and old iron. The only thing missing is a man willing to pick one up, turn it slowly in his hands, and learn what it has to teach.